Okay, so we have solved our first partial differential equation problem. Let's take the same one, well, same equation, but with some different boundary conditions. Okay, so let's maybe rewrite what we want. We want to solve du over dt is equal to some k d square u over dx square. Okay, so one variable, one space variable, and we want now to, well, we will still have some initial condition that would be the same kind, so u of x0 is equal to some phi of x, but we're going to change our boundary conditions. Previous ones were called Dirichlet boundary condition, and now they're called Neumann, von Neumann, no, Neumann, only boundary conditions, okay? And instead of being applied to the values, they're going to be applied to the first order partial derivative, so du over dx in 0t and is equal to du over dx in 1t, and that should be equal to 0. Of course, it's you could choose any other value than 0, but that's the idea. What does it mean? It means that you have no flux going out of your domain, all right? So means maybe your solution is going to stabilize to something like this, but the idea is that nothing goes out of your, no flux goes out of your domain. Right, so whether it's heat or concentration of whatever substance or anything. Okay, so remember we're solving that using separation of variables, meaning that we take u of xt being the product of a function of t and a function of x. What I propose you is that you try to do this by yourself, and you even have the solution here. Okay, so pause the video, do that, and come back here to see the solution, to see how we deal when you are done doing that. Okay, the videos of today are not too long, so you can really take the time to practice on that example, and it's really going to help you do the rest. Okay, so let us see how that is working. So we proceed exactly like before, meaning that our equation gets rewritten. Sorry, our equation gets rewritten. So du over dt is going just to give you t prime times x, and on the other side k times the d square u over dx square. So that's t x second. Okay, and we put all the t's on one side, all the x on the other side. So t prime of t, we can take the k with the t. It doesn't really matter because it would just change the lambda coefficient in the end, all right? But then it would be you would get exactly the same thing if you kept the k on the other side. All right, and that's going to be equal to x second over x. Same reasoning, so that's a function on t on the left, a function of x on the right. So the only way that these can be equal to each other for any values of x and any values of t is if they are equal to some constant, and we choose, because that's the right choice. And you should try to do the wrong choice to understand fully why this is going to be the right choice in that case. Okay. So minus lambda, well, lambda is positive. Okay, and we do the solving as before. It means that t prime is equal to minus lambda kt, so that t is, well, that just gives you a first order differential equation. T is just some constants times exponential minus lambda k times t. Okay, and on the other side I get x second plus lambda x is equal to 0. Characteristic equation is r square plus lambda is equal to 0. If lambda is positive, I've got two complex roots, plus or minus I square root of lambda, and that gives me that x of x is going to be a combination of cosines. So square root of lambda, sorry, times t plus times x. I'm really always doing that error. So square root of lambda times x plus c sinus of square root of lambda times x again. Okay. That's it. So then we're going to use our initial conditions and boundary conditions. So if I use my boundary conditions, which have now become where are they? Where are they? So which have now become the first derivative according to x in 0 and in 1 are equal to 0. Okay, right. What does that give us? So first derivative in x, that's just going to be so du over dx. Before applying the value of x is equal to 0, x is equal to 0 or 1, I must just compute it for any x and t. So again, that's just going to be t prime, t times t of t times x prime of t. So that's just going to be, well, t of t instead, whatever it is. Okay, we found it, but it doesn't really matter. Times, so the derivative of x with respect to x, because it's a function of x, so that's just going to be minus b sinus minus b square root of lambda, sorry, square root of lambda times sinus of square root of lambda times x, okay, plus c square root of lambda cosine of square root of lambda times x, and we get that for any t, we get that in 0. So du over dx in 0t, that should be equal to 0. So that means that t of t times in 0 the sinus disappears, okay, is equal to 0. So I'm just left with c square root of lambda cosine of square root of lambda times 0, which is 1. Okay, that should be equal to 0, and very similarly as before, well, we get that the only way that this is equal to 0 for all values of t is that if ever, so that has no reason to be equal to 0, and but this, we can still do something about this. So let's say that this is going to make c is equal to 0. Okay, if I take lambda is equal to 0, it's going to make it much harder to work because I would have something independent of t, okay, of the time when you plug lambda is equal to 0 in the t. Okay, so my only reasonable choice is to take c is equal to 0. So what's about my solution now? It looks like the x part without any sine component, so is equal to b times cosine square root of lambda times x. Good. So what we can do next is apply see what's happening in with the other boundary condition. It tells me that the flux on the right is equal to 0, so du over dx 1t is also equal to 0. So again, we get t of t. And now we knew that, well, c was 0, so only left minus b square root of lambda times the sinus of square root of lambda. Okay, and what does that tell me? It tells me, well, if I choose b is equal to 0, I'm going to have the same problem as before. That would make my solution constantly equal to 0, so no way to satisfy a non-zero initial condition. So that's not satisfying, so we should find another way to cancel that for every values of t, and so my choice is to take square root of lambda is equal to n times pi, so that the sinus is canceling. Right, so that's it. What do I get now for my solution? U of xt is equal to ae negative n square pi square kt times, I only have my b non-zero b stuff, so b cosine, so the cosine times b cosine square root of lambda is n pi x. Okay, so very similar as before, except that I kept the cosine part and not the sine part. What's the reasoning next is to say, well, that works for every values of n. So let's say that this corresponds to something, and even I can put the an and bn together and say, well, this is my constant cn, right? And so, well, not c because I've already had some c, so dn. And so that's anything written like this is a solution. So the sum of all solutions is going to be a solution. It's just going to be the sum of my un of xt from 0 to infinity. So here I can start at 0. Well, I could also start at 0 before. It's just that before, if I started at 0, yeah, it just gave me the sinus of 0, so that was cancelling. But here, cosine of 0 is 1, so that's interesting to keep it, and actually I'm going to need that. So this can be written as so my sum of dn coefficients times e minus n square pi square kt times cosine n pi x, okay, and I still have to find the values of the dn, and for this I'm going to use the initial condition, which tells me that u of x0 should be equal to some phi of x. So that means that phi of x should be equal to whatever I get for t is equal to 0. So the sum from 0 to infinity, dn. My exponential gets a 0 exponent, so that's going to give me 1. And I just have this one, n pi x. And what is that? This is really exactly what I would have if I wrote the cosine trigonometric series, well, Fourier trigonometric series, expansion of phi. Okay, so I've got my phi function. Well, sorry, I'm in between 0 and 1, so this is my domain between 0 and 1. I had my phi function doing whatever it does. It doesn't have to be equal to 0 on the sides. Just, well, I will have 0 flux on the outside. That's just it. And I'm doing some kind of even extension. Well, not some kind, exactly an even extension and periodization of my phi function that allows me to do the computation of my Fourier coefficients, and same reasoning as before. My Fourier coefficients, Fourier cosine coefficients of phi, they will all be given, including the I0. I saw correcting the midterm that it wasn't obvious for you that actually the formula for the I0 is exactly the same as the one for the AN. It's just that when you write it in the Fourier series, you divide it by 2. But that's you have these two coefficients, but because we really wanted to keep the same formula for the I0 as for the rest of the AN. And so that's my period obviously is going to be 2. So half a period is 1. Integral on a full period from -1 to of phi of x times cosine n pi x dx. And what else do we have? And that's going to be my dn coefficients. And then we just use the fact that this is a product of two even functions, so that's making an even function. And we do the same small simplification as before. It's just going to be 2 times the integral between 0 and 1 of phi of x cos n pi x dx. Okay, and this is what we obtain. Sorry, this is it. This is really what we obtain. Sorry. In that formula, that the an are the cosine decomposition coefficients of the phi function, okay, the one that we find here. Well, slightly different notations than the one that I've used in the calculation, but this is really what we get. And that's it. And so what do we get? We get that as t, that's very interesting to see, that as t tends to infinity, so that is just going to go to the exponential of negative infinity, so that tends to 0 as t tends to infinity. And so that sum part is going to cancel, and your solution is going to stabilize around around the mean value of the initial condition. Okay, so that's you started with some phi, and then you're going to stabilize because you want a zero flux here. So you want zero flux, so it's just going to stabilize around the mean value of your initial condition, right? Around the mean value of this initial condition. Okay.